Taylor and Maclaurin series. We already know that we could approximate this function sine x by taking a Taylor polynomial of degree n, and as we increased this degree, we increased our approximation here. But our question is, can we take a power series? So can we let n go to infinity and express this and have it equal a function? That's what we're interested in doing and figuring out what these coefficients would need to be. And first of all, if we took the nth derivative at a then, which is what we would do for a Taylor polynomial, we would move on this power series, we would move this n out in front, decrease the power by 1, we would do it again and again, and if we did the nth derivative, that would then give us n factorial and this c sub n. We could solve this for c sub n, and we would have then a formula for these coefficients in this power series, and it would need to be then our nth derivative at a over n factorial. So putting this together, if f has a power series representation at a, then this power series, and we're looking on this radius of convergence, then its coefficients would be given by this formula, and essentially it would be saying then that we would have these Taylor polynomials, but we would continue on and let n approach infinity. Now notice this says if. It doesn't say that it has a power series with these coefficients. It says if it has a power series, then these would be the coefficients. So let's go ahead and investigate this a little bit further. So we are going to have what we call a Taylor series centered at a then by using these coefficients, and so it's our power series but replacing this, and when we do that we see that these terms in this power series are the terms of our Taylor polynomial, but we're going to keep going with it instead of stopping at n. Now a special case of the Taylor series is when it's centered at 0. And if it's centered at 0, then this is just simply called the Maclaurin series. And we did mention that when we talked about Taylor polynomials. Taylor polynomials with a equaling 0 are Maclaurin polynomials, and these are named after Colin Maclaurin, who is a Scottish mathematician, and he used the special case of the Taylor series centered at 0 in his treatise. So can we find a Maclaurin series for the function f of x equal e to the x? Well, we could figure out the derivatives, and all of the derivatives, the nth derivative is e to the x, any derivative is e to the x. So if we evaluate any derivative at 0, we would have e to the 0 or 1. So if we were to write out these terms, we would have this, looking at these terms, we would have this would be 1. We'd have x to the n over n factorial. So does this equal e to the x is our question, and here are the terms written out. And if there was a Taylor series that equaled this function e to the x, it would be this function. But the big question is, does it equal? That's what we want to try and figure out. So the big if it has a power series expansion at 0, then this is what it would be. But how do we determine whether it does? Well, we would know that a function is the sum of its Taylor series if the function equaled the Taylor polynomials as we let n go to infinity. So let's explore this idea. We know that the remainder is the function minus the nth degree Taylor polynomial. We could take this and we could solve it for the function. So the function is going to equal the nth degree Taylor polynomial plus this remainder. Now we want to then look as n goes to infinity. And so if we'd looked and we said we need the limit as n goes to infinity for this Taylor polynomial and for this remainder, we know that f of x needs to equal the limit as n goes to infinity for this function to equal its Taylor series. So we can replace this side with the limit as n goes to infinity of this, and then these would cancel and leave us 0. So this basically tells us that we would need as n goes to infinity for this remainder to go to 0. And so if the limit as n approaches infinity, the remainder is 0, then the function would equal its Taylor series. So let's put this in a theorem. If we have a function and it equals a Taylor polynomial to degree n plus the remainder, and the limit as n goes to infinity, the remainder is 0 for x within this radius of convergence, then f is equal to the sum of its Taylor series. So here is our requirement for a function to equal its Taylor series. Let's then go back and explore whether e to the x equals its Taylor series. So one of the things we know is the limit as n goes to infinity of x to the n over n factorial is 0 for every real number. How do we know that? Well, we looked at this series and we found that this series converged for every real number. It's been a little while, but remember how we did that? Maybe we'll quickly do it so we can remember. We used on this the ratio test, and we looked at the n plus 1 term and we divided it by the nth term. And we've got the absolute value there. And so this would cancel here and leave us x. This would cancel here and leave us n plus 1. And we're looking at the limit as n goes to infinity to apply the ratio test. And so that would equal, we can take this absolute value of x out in front because that doesn't involve the n. And then we have the limit as n goes to infinity of 1 over n plus 1, and for this to converge we know that we need this less than 1, but it is 0, so this goes to 0, and so this converges for every number x. Well, by the divergence theorem, if this series converges for every number x, then the limit, looking at the terms, is 0. So the terms have to go to 0 if this series converges. So we know that this is true, and we're going to come back to that in a minute. So let's prove that e to the x equals the sum of its Maclaurin series. So if the function we're looking at is e to the x, then the n plus 1 derivative, or every derivative, is e to the x. And so if we have d being a positive number such that the absolute value of x is less than or equal to d, then we could express this derivative, its absolute value, since we know it equals e to the x, as less than or equal to d, since our absolute value of x is less than or equal to d. So here we have an m. We've got a bound on our derivative. So by Taylor's inequality, and we have a equaling 0, we've got our m, and we can put that in here, and this is just simply Taylor's inequality. So we're looking at our remainder here, and we have a bound on it. Now let's look at this expression as n goes to infinity, and as we look at that, we can bring this e to the d out in front, and then we have this piece right here. But wait, we just showed that that goes to 0. So we can actually squeeze this remainder then in between our two functions that are going to 0, and by the squeeze theorem this remainder is also going to 0. If the remainder is going to 0, then it means that this function equals the sum of its Maclaurin series. So e to the x does equal infinite sum, x to the n over n factorial for all x. In 1748, Leonhard Euler used this equation, and so he was able to find the value of E correct to 23 digits. In 2007, Shigeru Kondo used this equation to compute E. Now obviously he's got lots of computing power now, but he's computed it to more than 100 billion decimal places by using this power series. Interesting. So let's see, finding the Maclaurin series for sine x. Well, we already found the Taylor polynomial of degree 7, And so we can use that and just add our dot dot dots, and we will have the Maclaurin series for sine x. Now if we want to express that in terms of a power series notation here, we're going to have n from 0 to infinity. We need something to alternate the sign, so we have -1 to the n. We're starting with 0, so this will start with positive and then alternate from there. We need odd powers here, so 2n plus 1 will generate, as we put in 0 we get 1, as we put in 1 we get 3, and so forth. So this will give us these odd powers. This will give us these odd factorials for the denominator. So let's find the Maclaurin series for cosine x. It's Maclaurin series, so we know it's centered at 0. So we're going to need some derivatives. F prime of x is going to be negative sine x, and evaluating that at 0 is going to give us 0. F double prime of x is going to be negative cosine x. Evaluating that at 0 is going to give us -1. F triple prime of x is going to be sine x. Evaluating that at 0 is going to give us 0. And the fourth derivative of x equals cosine x. Evaluating that at 0 will give us 1, and then we've got our cycle. So as we want to express this, f of x, we first need the function at 0, that's 1, and then as we get to the next coefficient, that's 0, and as we get to the next one, it's a negative, so this is going to be x squared over 2 factorial. Next one is 0, next one is positive, x to the 4th over 4 factorial, and we see the pattern here, x to the 6th over 6 factorial, and so forth. So we can express that as this, and let's see if we could figure out what this would need to do then to express this as a sum. We have n going from 0 to infinity. We need to alternate signs, and as we start with 0 we want it positive, so we could put that to the n. And then we want x to the positive power, so 2n would do that, over, and then if we had 2n factorial. So here is our Taylor series and Maclaurin series, which is just our special case of Taylor series centered at 0 for cosine x. What if we wanted to find the Maclaurin series for x cosine x? So as we think about this, how is this different than what we did? Well, it was our original function multiplied by x. So we could take this and we could multiply it by x. So if we want the power series for x cosine x, that's going to be the sum as n goes from 0 to infinity, -1 to the n, x to the, we multiplied this by x, this is to the 1, so this would be 2n plus 1 over 2n factorial.